The core physics concept to the galvanic series we'll see. The entire concept relies on the galvanic series, that is electromotive series, which ranks the metals according to their electric potential. So some metals may be having higher electric potential, some metals may be having lower electric potential. So galvanic series is the one that ranks metals according to their electric potential. So anodic versus cathodic, you will see when two different metals are connected in an electrolyte like seawater, the metal with more negative potential higher on the series becomes the anode and will corrode. Corrode means oxidize. The metal with more positive potential, that means lower on the series, becomes cathode and is protected. That's reduced sacrifice. In marine cathodic protection, if you see the structure, the steel acts as a cathode, the protected metal. The anode, that is zinc or aluminum or magnesium, these metals are chosen because they are much more electrochemically active than steel, because these things are much more electrochemically active, and they are deliberately given the more negative potential. How it works in the redox reaction: the protection process is controlled flow of electrons driven by the potential difference between the two connected metals. So the protection process is a controlled flow of electrons. Electrons is flowing from the anode to the cathode. So anodes are easily giving up their electrons because they are more electrochemically active than steel. So oxidation at the anode. Oxidation happens at the anode only. Oxidation means corrosion. The anode metal zinc oxidizes, that means loses electrons more readily than steel. That means the bond is weaker in the cathode. That's why it's easily giving up its electrons. The zinc atoms change into zinc ions. Zinc becomes zinc ions inside N2 plus and dissolve into the seawater. This is the sacrifice. The reduction of the cathode protection. The electrons released by the anode travel through the connection, the structure to the steel surface. And this influx of electrons forces the steel surface structure to become entirely cathodic, preventing rust. Because the steel is constantly being supplied with electrons, it cannot undergo oxidation reaction necessary to form the rust. So oxidation reaction, this is oxidation reaction, it cannot undergo because it's continuously filled up with electrons from the cathode anodes. Instead, the electrons are consumed by the dissolved oxygen and water in the seawater, right? So turning oxygen into hydroxide ions. This process is known as polarization. You understand? How is the rust is being prevented? The steel is being constantly supplied with influx of free electrons, right? These electrons are coming from the anodes. So those electrons, that means like the steel cannot undergo oxidation reaction necessary to form rust. When is rust getting formed? Once the oxidation process happened. What is oxidation process? Oxidation process means the steel, if it loses electrons, that's oxidation process, that's a corrosion. But it's not losing its electrons because it's already getting the excess amount of saturated amount of electrons from the anodes. Instead, the electrons are consumed by dissolved oxygen and the water in the sea. So that free electrons are right, the 2 electrons that's getting reacted with water and oxygen, that's turning into hydroxide. This is the hydroxide ions, OH. So this process is known as, because of the polarization process, it's getting protected. In short, the sacrificial anode uses higher energy state, higher chemical activity to create closed circuit that steals the corrosive energy of the environment away from the valuable steel structure. Now let's have a group discussion. We will go through that group discussion we had with Mr. Davis and team. Right, listen up you lot. We are discussing the cathodic protection. What's the biggest worry for a steel hull in the sea? What's the biggest worry for the steel hull in the sea? Corrosion. Correct. What is corrosion? That's rust, technically yes. But what's causing it? What's causing the corrosion? I mean rust. Isn't the sea an electrolyte? Yes, the salt water makes the steel lose electrons, doesn't it? Precisely. But how do we stop the steel from losing its electrons? How do we stop the steel from losing its electrons? We give it something else to lose. Excellent. We introduce the sacrificial anode. Look at this block. That's metal. Zinc mostly, isn't it? Aluminium. Good. Why zinc? Why not more steel? Because zinc is more electrochemically active. Zinc is more electrochemically active. What does that mean? Explain it and simply. It means the sea wants to eat the zinc first, doesn't it? It's like zinc has a much more weak electrical bond. Doesn't mean that make the zinc the anode. The zinc is the anode, so it oxidizes and sacrifices itself. So zinc is the anode, it oxidizes and sacrifices itself. So what does the steel hull become? That becomes a cathode. It's protected. So right, the electrons from the dissolving zinc flow straight into the steel. What does that flow from stop from happening? It stops the steel from getting enough charge to turn into rust, doesn't it? It forces the corrosive energy onto the zinc. So what happens to the zinc block over time? It gets eaten away. It has to be replaced. So the zinc block gets eaten away, it has to be replaced. And why is the replacing small zinc block cheaper than welding the new hull plate? Because it saves the whole structure, doesn't it? A small cheap sacrifice, a simple application of redox physics. Let's go a bit deeper. Shall we use? You have all passed your foundation modules, but the reality is here right now on this call. We protect the steel structure with cathodic protection. What's the fundamental principle at work? We are changing the steel's electrical state. We are changing the steel's electrical state. We turn the whole hull into a cathode so it can't rust. Excellent. How do we force this expansive huge hull become a cathode? We attach something else. What is that something else called? What is its specific job? What is its specific job? It's a sacrificial anode. It is meant to get eaten by the sea instead of steel. A decoy? A decoy indeed, but scientific one. What is the chemical term for the anode getting eaten? That's oxidation. Zinc loses its electrons, turning into positive ions that float away. Precisely, it's furious intentional oxidation. Where do those released oxygen electrons go? Where do those released electrons go? They don't just vanish into the deep blue, do they? No, so they travel through the connecting wire and spread out over the steel surface of the hull. They need a path. And rush of fresh electrons flowing into the steel hull. What is the effect of that? Why doesn't the steel start to oxidize and rust? Because the electrons are already there, they fill up the sites where corrosion would start. The steel can't lose any more charge, so the whole reaction stops for the hull. Here grabs the core concept of polarization. The anode sacrifices its own mass and energy to keep the hull saturated with electrons. What dictates which metal sacrifices itself? Is it just a luck? No. No, it's the position. It's their position in the galvanic series. And zinc and aluminum are more active than steel, so they always corrode first in the electrolyte. The galvanic series is a simple electrical hierarchy. We deliberately pick a metal with an anode that has a higher, more negative potential than the steel. So what happens when we inevitably have to send the divers now next year? They'll find the anode is half gone and they will have to bolt a new fresh one in its place. It's just a maintenance. A small necessary cost to prevent the catastrophic structural failure. It's applied electrochemistry. Any further confusion? Alright, let's discuss the simplistic analogies. We are discussing the controlled corrosion. Define the thermodynamic requirement of the steel hull to actively resist oxidation. The steel surface potential must be shifted to cathodic range. We must establish a protective current density. How does that sacrificial anode specifically achieve this essential shift? What is the core physics principle at play? It exploits the potential difference derived from the galvanic series. Zinc possesses significantly more active standard electrode potential compared to the passivated steel. The zinc becomes the anode, the steel becomes cathode. Describe the Offshore reaction occurring at the anode surface in the chloride-rich environment. Electrolyte. This zinc undergoes oxidation. This generates necessary driving voltage for the protective current. Precisely. Now the SAM track those electrons. What is the fundamental reaction occurring at the cathode that prevents ion from oxidizing? The external electrons are consumed by cathodic reaction, chiefly reduction of the dissolved oxygen and water. This reaction sustains the protective potential. Excellent. The generation of these hydroxyl ions at the steel surface aids calcareous deposition, a beneficial secondary barrier. What is a critical operational constraint we must monitor to ensure the system remains effective? We must ensure the current density supplied by the anode is sufficient to polarize the entire exposed surface of the steel. So, whatever the current density is supplied by the anode must be sufficient enough to polarize the entire exposed surface of the steel. If the anode's output drops due to consumption or if resistance in the circuit increases, the potential decays and localized corrosion returns. The anode must supply the required charge capacity for the specified design life. Anode must supply the required charge capacity. When the anode's mass is sufficiently depleted, the driving potential falls and the circuit's effectiveness collapses. Why is the monitor anode consumption and maintain the required replacement schedule?